Hello, class. Today, Chapter 9, Section 2, Area of a Triangle. Well, we know that, I'm sure you know that the area of a triangle's formula is 1 half base times height, uh, 1 half b times h often. Um, but, um, so, obviously that's pretty easy. You should know all of that. But we're going to be finding areas of triangles, not given the traditional base and height. But just before we get started, we're going to change this formula a little bit because of the fact that A is used to represent angle A often. We don't want to get that confused with the letter A. We don't want this capital A to be confused between whether that means area or the angle A. So we're going to go ahead and switch that up with the most logical next letter to use, and that's K. I'm joking. I don't know why they use K, but they decided to use K. So instead of A, we're going to say K is the area of the triangle, okay? And so area of the triangle, K, is equal to 1 half base times height. Okay, typically, so for instance, in this case right here, what we're looking at in this triangle down here, our base, that's another thing. B is often means to one of the sides of the triangle is B, and it's not always the side that we consider the base. So in this instance here, the base is A of the triangle and the height is H. Every single side could be the base if we had a height for that side, okay? And the height is always exactly perpendicular with the base. So if we knew this side here, if we knew the height, which would be a line that would go probably like this, where my hand is, that would be outside the triangle. We could say that this is a base and that's the height and find the area. But in this case, we have A as our base because we know the height that goes this way. So so the height always goes from the side, is the perpendicular line that goes from the side, that's the base, to the opposite vertice, the vertice that's not part of that side. Okay, that's what's going on here. So that would be our base, that would be our height. Okay, so in this case, our base is A. That's what this is here, because that's the side A, and our height is H, which is this length that's not one of the sides. Okay. So we might not normally be given the height though, but if we would know this angle measure over here, we would have, see this right triangle here? See that? So we could actually find this height if we would know the angle measure, because we could do sine. If we would know, we'd also need to know C, so we'd have to know some information more than, just one thing. But if we knew C, and we knew this angle measure, we could actually find the height using sine, because remember, sine is, so this triangle right here, the hypotenuse is C. Sine is opposite over hypotenuse. So if this right triangle here, we have an opposite and we have a hypotenuse, so we would be able to find the height, which is part of that formula, if we knew B and C, angle B and side C. Okay. So we're going to rewrite this with C over here. So our height is actually going to be, or so what we can do is we can find the area of, so in general though, let me just take a step back, sorry. So in general, if we would solve this for H, the height, we would multiply both sides by C. And so we would have C, this side, times this angle, okay, would be our height. And we can actually take that and substitute that in right here, okay? So this area formula that we had, 1 half base A times height, can be rewritten as 1 half side A times side C times sine of B. Okay, so now we can actually find the area of any triangle if we have two sides and the angle between it. Do you see that? How we have A, we have C, and we have the angle between it. Okay, so we would just need two sides and the angle between it, and we can find the area of any triangle. Okay, using this formula, because this part's the height, this is the base. Okay, and it actually would work for any of the sides, any two sides given and the angle in between it, and we can find the area, because we could go through that entire same process with two other sides, okay? the same entire process, but we could sorry, it's the entire same process. So we could use any of these formulas to find the area of a triangle given two sides and the included angle. You notice that so the way the letters work, I don't know if I emphasized this before. When we were doing this last section, I should have made that clear. That so when we label an angle A, the side that's capital A. Little a is always opposite that. So angle B is always opposite angle. Sorry, angle B is always opposite side B. Side A is always opposite angle A. And C, so they always match that way. So you'll never have an angle touching the same letter that it is, okay? Because A is going to be made up of this side and this side. Okay, so side A is going to be opposite. So if you're looking at these, you'll notice that you will use whichever one you have the information for, but it's always going to be all three letters. Two of the letters are going to be so like A, B, C, A, B, C, A, B, C. See that? So it's going to be two of the sides and one of the angle in between them. So hopefully that makes sense. So we are going to do an example. Surprise, surprise. So two sides of a triangle have lengths 8 and 5. The included angle, the angle between is 53 degrees. Find the measure. They don't actually give us letters in this case, but we don't need the letters. So this is a little kind of a sketch here of what's going on. We don't know what the triangle actually looks like, but you can just kind of, well, I mean, you can figure it out if you measured it well. So using this formula here, we have the two sides and the angle in between. So we can just plug in without needing to label the angles and sides. We can just plug straight in. So 5, 8, and then 53 degrees. 1/2, obviously don't forget the 1/2. 1/2 times 5 times, 1/2 times 8 times 5 times sine of 53 degrees. So 1/2, 8, and 5, two m's make m squared. So that would be 40, and half of that is 20. And then sine of 53 degrees, you do that on your calculator. Do 20 times sine of 53, and you get approximately 16. Let me do that because I don't think in this section I've used the calculator yet. No, because this is the first example. So if I had 20 times sine of 53, 20 times sine of 53, this is before I hit enter, I'll make sure I'm in degree mode, and 15.97, which rounded up to 16 with one decimal place. And one decimal place is fine for solving triangles and finding the area. Okay. The area of a triangle is 20. So in this case, they tell us that the area is 20. If A is 6 and B is 12, find all possible measures for C. Okay. So notice how the lettering matters because they're looking for C. C will be the angle between these two. I know that because side C is opposite angle C, right? So A and B must be the other two angles, or other two sides that make up this angle. So we can use A, B, and C then, the formula with A, B, and C, angle C. We're plugging in for 20. We're plugging in for K, 20 for K, and then 6 and 12. So 1/2 times 6 times 12, that would go to 36. So we're going to divide both sides, okay? Simplify that to 5/9. To solve this for C, to find an angle, we would do sine inverse of both sides, right? Everybody with me so far? So sine inverse, here's where it gets a little tricky because you'd be very tempted probably just to do sine inverse of 5 divided by 9. Just to remind you, second sine is sine inverse, and we get 33.7, okay? But when it says find all possible measures, here's what's going on. Remember, that's a first quadrant solution, and there will be a second quadrant solution for that. So the reference angle would be 33.7. I'm not going to make you show the reference angle in this case. The reference angle formula is 180 minus theta, so then we solve for theta, and we switch that around, flip the alpha into theta in this case, and then we do 180 minus second answer and get 146.3. So what does that mean? Well, there's actually two different angles, two different triangles with this side length, that give you angle measure or area measure. Total of area of 20. And I can actually show you that by going back here and I think I kind of fit this right here between the camera and the work. And again, we're rounding these numbers. Well, actually, I wouldn't. I could actually just select them from up here. So I'll do that. So I'm going to do 1/2. Okay. Yeah, times. Actually, let me start over. Let me put that in parentheses just so it's clear. 1/2 times, and then I'm going to do 6 times 12. And then times sine of this angle measure here. Went up and selected it, and I get 20. Okay. I'll do it again. Do another one. 1/2 times 6 times 12. Two sides, and then if the angle measure in between is the second thing we got, the second quadrant solution, it also gives me 20. So there's actually two options. There's two different angles that could be that give me a total area of 20 for this triangle for what they gave us. Okay. But say like if I tried putting something else in, like if I just tried putting in, let's say it's, I don't know, 80, you'll see that triangle would give a different value. It's a different measure, different area. So there's, it's possible to have two different angles. I hope you can imagine that two different triangles can have the same area, right? And then these restrictions don't make it aren't so stringent that there couldn't be more than two angles, or sorry, more than one angle that would give that same area. But do note that you won't ever have to do this and find a third quadrant angle. And that's because it won't ever be the case that there's a third quadrant angle that you have to find, or a fourth, because these work because these are both under 180, and all three angles have to add up to 180. This is not a right triangle. We're not doing right triangles, so you have to worry about the 90. So all we know is that we have, for this first answer, we would have 180 minus 33.7. So we would have 146.3 degrees approximately to split between the other two angles, right? And then 180 minus, 143, right? So we're going to have 33.7 degrees to split between angles A and B. Well, that's enough to split. I mean, it's small, but it's still enough to split. But if we would go into the third quadrant, we would be over 180. You can't have an angle over 180 in a triangle because all three have to add up to 180. So hopefully that's making sense. So you'll never have to go into the third quadrant for a problem like that. That's my point. So continuing this section in the same video, because last time I split it up and the second video was only like a 3-minute video. Find the area of the following quadrilateral. Look at this thing. Okay, so this is not a triangle. It's a quadrilateral, but there's a thing about quadrilaterals. All quadrilaterals can be split into two triangles. Every single quadrilateral can be split into two triangles. And then every single pentagon can be split into 3 triangles. Every single hexagon can be split into 4 triangles. This is just this property about polygons, that you can always break them into smaller pieces, all that are a bunch of that are all triangles. So it all goes back to triangles, I guess, is the point. So that's what I'm going to do. I'm going to split this into 2 triangles. It can often be very difficult to decide how to split it because there's more than one way to split it. Split it this way, split it this way. Okay. If I split it, so for quadrilaterals, there's 2 ways to split it. So if I split it this way, there would be some problems. We are helped immensely by the fact that there's a right angle here, because that makes splitting it this way a right triangle. Without that right triangle, if I would split it this way, I would break that right triangle angle. Sorry, I would break that right angle, and so I would lose it. I would lose that ability to use that right angle. But if I split this way, I keep that right angle. I'm liking that right angle because I'm given this here, I'm given this here, and I'm thinking, oh, I can use Pythagorean theorem to find the middle here. Okay, so that's what I'm thinking. So that's why I'm thinking I'd split it that way. Okay, so if we can find the area of A, and then we could find the area of B will be the goal. Um, so how do we find the area of A? Well, we have two sides and an angle in between, right? And in fact, if you think about it, this right triangle here, you can just use base times height, 1/2 base times height, because sine of 90 is 1, right? We learned that when we did the curves. So this actually just goes to 1, and this is a base times height situation for this part of the triangle. But to do it with the way we've been doing it, you would do sine of 90, that's the angle in between these two sides, and we would get 20. That is kind of it's kind of neat to see how that actually works this way with our formula. One, you wouldn't have had to use it, but it's still functional with everything that we're learning. Okay. So going to the whole thing that I was getting into a minute ago is finding the area of B. That's going to be the tricky part. How do we find the area of B? So we're going to, that's where I'm going back to what I was saying about the Pythagorean theorem. We're going to use Pythagorean theorem to find this dashed blue line. Because it's a right triangle, we can use that. 5 squared plus 8 squared equals c squared. So 25 plus 64, that's 89. So about approximately 9.4. We found this to be approximately 9.4. Okay. So that's nice to know, but we don't know this angle quite yet, because this 75 is both of these. We broke that 75 into two parts, right? However, we can find the part that's down here because we know the stuff over here, and it's a right triangle. So because we know this, when I say this stuff, sorry, well, we know that 5 and 8, we know 5 and 8, and this is a right triangle. So tangent of this part, this angle right here, the part of the 75 that's on the lower triangle. So tangent of that angle is equal to 5 over 8, opposite over adjacent, and we do tan inverse, and we find that to be approximately 32. Well, that would leave 75 for the other part of, or 73, sorry, for the other part of the angle. Now, I know I was saying don't use approximations, don't reuse approximations. Well, remember I said that don't do that if you can avoid it, and we're entering into areas where we have to use approximated values to find other things, because there's no other way to do it. So just keep that in mind when I said, and don't think that you can never use approximated values. I want you to avoid using it if you can, and there's a lot of places you can, but there's also a lot of places you can't. So just make sure, just be wise about that. So we found 43, approximately 43, to be this angle here. So now we have we have two sides and the included angle. Now I want to show you something to do here when you have to use approximated values. This is very important. So when we have to use approximated values, I want you to do something. So I would have to take the square root of 89 in my calculator. I didn't show you that, but that's how I would have gotten 9.4. I mean, I could have maybe mentally gotten around that, but I wouldn't have trusted that I wouldn't have trusted my decimal value. So I put that in my calculator. So I get 9.4. So what I want to do with this value, because I'm going to be reusing it later, and I'm also going to be reusing another value. So you can use this button. This is a very powerful button on your graphing calculator. It's called Store. And once you have the value you want to store as the last answer you got, you can click that button, and you hit this alpha button. Will open up all the green. In your graphing calculator might be different colors, but all these green buttons for me, all these green letters for me, are now accessible. And because this is a value of C, I'm going to fill that in for C. So what I just did was I stored this decimal value into the letter C. Anytime I press letter C, alpha C, I get that decimal value. Now, most of the time, these are filled with zeros to start. Like, all these letters are storage spots for numbers that you want to keep. And there'll be zeros by default. If you never fill them up, they'll just sit there with zeros. But now that I put something in for C, I now have that decimal value in for C that I can retrieve. Because I should use even though I write 9.4, and you don't have to write all those decimal values, when you're actually doing the calculations on your calculator, you should use as many decimal values as the calculator can handle. Okay, so let me just say that again. You only write part of this, but you should try and use all of this. Okay, you should try to use everything you can, and you can use everything the calculator can store. So now I'm going to go to the tangent inverse of 5/8. Okay, and this is what I would have done down here to get 32. So see how it's 32.00? That's why I didn't put 0.0 like I said. I should have done that. But so 32.0. So what I was just saying a second ago is usually when I approximate, and even if it's a 0.0, I often put 0.0 just because like this doesn't look like it's an approximated number to me because it's an integer. But that's something I failed to do there. But so I want to. But now I'm putting this apparently into x. So let me just check my x value before I do this. Yes, it's 0. So now I got to go do this again because my last value is no longer the one I want to store. So alpha x. I chose just a variable x. I split this angle here into x and y. That's what happened. So actually, so then 75 minus x that's where I got the 42.99, rounded up to 43. Okay, and now I'm going to alpha store that. I didn't really need to store the x, I guess, because really what I need is the y, alpha y. So I just chose x and y randomly, just because I wanted to use something. So x plus y is what equals the 75, just in case you're wondering. Okay, so now I have those values stored in my calculator, and I can come down here, and to find the area B, this part of the triangle B, I'm going to do 1/2 times, and I wanted to check what I did, so times, I see that I just jumped down. I didn't know how many steps I should. 14 is a nice and clean number. I didn't store that anywhere, times. And then 9.4 was what I stored in for C, because I chose C just because of the fact that it was the hypotenuse, and a squared plus b squared plus or equals c squared. Whew, I'm tired. And then I need to do sine of, and then I said that was y, alpha y. And I got 45.0. Again, I should have put a 0.0 there. Okay. So so first of all, I wanted to show you how this is done, but also emphasize the fact that you should be using as many decimal places as the calculator carries when you do use rounded answers, even though you only have to write one decimal place down. Okay. And we are not done yet. Wow. Whew. Almost missed that. We found the area of A to be 20. We found the area of B to be approximately 45, even though I didn't put the 0.0 there. This is approximately, and you have to add those together to get approximately 65. Remember, if one part is approximated, it doesn't matter how many things you're adding together. If one's approximated, it brings the whole thing down. Weakest link stuff going on there. Okay, so now that was the area of triangle using trigonometry. So there'll be some bookwork, and yeah, section 2 of chapter 9 done. Thank you and good day.